Hi students, today we are discussing the basis and the dimensions of a subspace in a subset and in the easiest best. Well, the depth of this content is largely taught and entertained in the linear algebra class, and before I do it, in a certain defined circumstances, please make sure that you subscribe to the channel for more mathematics content in a Mzansi context. You'll agree with me that when you deal with the basis and the dimensions, in fact, linear algebra in its entirety, you need to know your definitions and your theorems as well. So I have a mini definition of a basis that I want us to entertain in order for us to be able to do the cosmetic example, the one that I have just right here with me. Well, we are saying a set of vectors S, which is V1, V2 up until your Vn, in a vector space V is called a basis for V if the following conditions are true. So here you have two conditions which you must satisfy. And the first one is that S span V. That means you must be able to write your S, which is primarily your subspace. You must be able to write your subspace S in a linear combination. Is the concept spanning set here. So if we say S span V, we are primarily saying to you that you need to be able to write the set of vectors V as a linear combination, but those, they come from the subspace, which I presume that you are well inclined and well briefed with the linear combination and the linearly independent and dependent. All right. So number two, we are saying S is linearly independent. All right. So those are the two conditions which you must prove in order for you to really form a basis of a particular subspace in a subset. So when we talk about linearly independent, we are talking about a homogeneous equation which is going to have a trivial solution. Please get that? It's going to have a trivial solution. That means your x1, x2 up until your xn is really going to have a null solution, which is a zero. All right. So when we talk about the dimensions, here we are primarily talking about the number of vectors they are in a spanning set. So it means you need to get a spanning set unless if you are dealing with the basic one, the standard subspace, which I presume that you know. By that I mean, let's say maybe you have a vector x in your R4. Maybe let's just say in R3 for that matter. So this particular vector x, it really span a set of vectors. In fact, let me just put it in this way just to avoid confusion. This vector x in your R3, that means you're going to get x1, x2, and x3. All right. That is a set of vectors in R3. So this situation, it spans three vectors, and that is your x1, you get your 1, 0, 0. This one is called the standard one. And then a plus your x2 there, and then you're going to get a 0, 1, 0 there, and then a plus your x3, that is a 0, 0, 1. That is in your x3. But once we give you the algebraic specification, you need to be very careful. All right. So this one, they span and they are linearly independent. I hope you know that situation. Now, check this one. They are saying to you, determine the basis and the dimension of the subspace defined by W. So W is a subspace. You can also see that there is a zero vector here as for the conditions of a subspace. You must take your zero vector and it must be true for this algebraic specification. All right, but I'm not here to talk about subspace. You know how subspace work. I want us to find the basis. So first thing first, I need to be able to write S as a spanning set of vectors V. So let's check how you do that. You are going to say to yourself now that Let your x, the vector x, be in R3. This one is in R3. It's a vector x, it's in R3. Let me just emphasize this. The W is a subspace where this x is a vector and this vector belongs in R3. You can see that this one is in R3. Such that, this slash, it means such that your x2 is a basic variable because it is made the subset of the formula and it is equals to twice x1 plus x3, where x1 and x3 are primarily free variables. I hope you know the difference between a basic variable and the free variable. So x1 and x3 are primarily free. They are your parameters if you are to get the solutions in there. So this would then mean that you will then say to yourself, the vector x is going to be equals to, it's in R3. So you're going to get x1 and then x2 and your x3. But you have two variables that are free. And that is x1 and x2. All right, check. So your x1 and x3 are free. So you're going to write x1 and then x3, it's also free. But x2, it's a basic. So I'm going to say, well, x2 is given here. That is twice x1 plus x3. So I'm going to say this is twice x1 plus x3 just right here. And then now you just need to really write that as a linear combination of vectors. Pay attention. You're going to say, well, this is the vector x is equals to. You can see that you have x1 and what and your x3 just right here. So you can break that apart to say that is x1 and then a twice x1. There's no x1 in the last one. And then a plus, you're going to have a 0, there's no x3 in the first entry, and then you're going to get x3, and then you're going to get x1 there. So this basically is the sum of column, which must give you that one if you add them back. So I hope that algebra you're also inclined with it. So I'm then now going to say to myself that this situation, I can take out my x1 because this really seems like it's a scalar multiplication of column vectors. So that is going to be x1, and then you get a 1 to 0, and then a plus. You can take out your x3 here. I think I need to write x3 here. I made a blunder for that. So this should be x3. This is x3 I'm talking about. I hope that you will forgive me for that. So now you're going to get x3 just right here into your same stuff here. You're going to be having 0, 1, and then 1 there. So you will see that the vector x, which is this one here, this x here, it can be written as what? As a linear combination. You'll bear with me that this is a column vector, and then this one is a real number, and then this one is also a real number multiplied by a linear vector. So that means we managed to write the vector x in this fashion. That is x1 multiplied by v1 plus x3 multiplied by a vector v2. We call this situation a linear combination. But if here it was 0, it means it was going to be a homogeneous system, and it was going to lead you to a trivial or a non-trivial solution. So in this case, we can be able to write the vector x as a linear combination. So this tells us that the subspace W span a set of vectors, and those vectors are primarily these ones. These are your vectors that are being spanned. So therefore, I'm now going to say to myself, now that W span those vectors, that is 1 to 0, and then you're going to also get what? 0, 1, 1. So these vectors, they span a set of vectors V. So that means you manage to satisfy this particular condition. You now need to also show them that the set of vectors are linearly independent. So here, there are more of ways to show that vectors are linearly independent. The first one, let me just say, well, this was the the first part of it. It was the issue of spanning. We are now going to check if S is linearly independent. There are many ways to really do that. So you're going to have your S as set of vectors, and then that is 1, 2, 0. This is S, and then 0, 1, 1, which are basically these vectors here. So you want to check if these vectors are linearly independent. Like I said, there are more of ways to check that. One way would be to say the vectors, if they are a scalar multiple of each other, they are going to be linearly dependent. If they are not a scalar multiple, then they are linearly independent. I hope you also know that. But there is also a sweeping way to do that. That is to say, well, if when I have the homogeneous equation like that, if this equation, it can give me homogeneous, it can give me trivial solution. That means I'm going to have a linearly independent situation. So I'm going to do this by means of matrix, which I assume that you are inclined with it. So therefore, this is going to be these vectors augmented with a zero vector. And that is going to be 1, 2, 0, and then a 0, 1, 1. You need to really augment that with a zero vector. And then let's see what you're going to get there. This is really easy, eh? It's basically first year now. So you're in second year, but they take you back to first year. It's really easy. Check what you will do. You will reduce this matrix into a reduced row echelon form. And if you are to do that, you will agree with me that you're going to get, let's see, you're going to multiply this row by negative and add it with this last row in your operation. So it means you're going to get a 1, 0, 0, and then a 0, 1, 0, and then you're going to get a 0, 0, 0. And please, you must not get no solutions, because when you deal with a homogeneous system of equations, you do not have no solutions. This is homogeneous, so you do not have no solutions. You either have a trivial and non-trivial. But when you deal with linearly combination, that's where you're going to have no solutions depending on the system. All right. But for this one, there's no way where you'll arrive to a no solution situations. I hope that is clear to you guys. So you can see that now x1 is equals to x2. They are both equals to 0 from this one, and then also that, and then it's going to equals to that one. So these guys are really zeros. So the solution, we call this solution a trivial. So I'm going to say, well, therefore, the solution is trivial. It's trivial. So what do we know about trivial solutions? Those have a linearly independent set, all right? So I'm now going to say, therefore, the set is, so my set, which is a 1, 2, 0, and then the other one is 0, 1, 1, is linearly independent. So this is linearly independent. So that set is linearly independent. Or the other way to check that was you were going to really compare this vector and this vector. If they are not a scalar multiple of each other, then they are going to be linearly independent. But if they are, then they are going to really delete one row. That means it's going to make it to be linearly dependent, you know. So now you will see that you have an independent set. All right. So what you're going to do is you're going to say to yourself, if the set span V, which are basically these vectors that you saw that they were being spanned there. And then you also need to check linearly independency. So you can see that the two conditions are satisfied. That means that those vectors, they form the basis. All right. So I'm going to say, therefore, the vectors, the set of vectors that is 1, 2, 0, these vectors, which is 0, 1, 1, and then form a basis for W, which is your subspace. So now you need to get your dimension. This is very easy. This one, you don't have to really struggle. So with your dimension, you basically say the dimension of the subspace, which is W. You are going to count the number of vectors there are in a spanning set. So you go back to your spanning set. How many vectors are here? You have 2 of them. You've got 1, 2 there. So those 2 vectors, they give you the dimension of the W. So you're going to say, well, the dimension is primarily going to be equals to 2. And this is how you're going to solve this one. Thank you very much for watching. And please, guys, don't forget to subscribe to the channel for more mathematics content in Mzansi. And please comment the section which you want me to discuss here on YouTube, and then we'll take it from there. I'll be reading to your comments. Please, guys, comment and specify what is confusing you. I will make a video for that, and you'll really get it in the most autonomous manner possible. Thank you.